The red calling. Why Mars is our next home. The reddish glow of Mars speckling the vast night sky has always sparked curiosity within us. For millennia, it was a god, an omen, a distant mystery. Today, on the threshold of a new era, Mars is no longer just a point of light. It has become a beacon, the next great frontier for humanity. But why are our eyes so firmly fixed on this desolate planet? The answer is complex, multifaceted, woven between the fundamental need for our species to survive, the insatiable exploratory impulse that defines us, and the promise of a limitless future that resonates in every fiber of our being. The survival of the species, an essential cosmic plan. Our home, Earth, is a shimmering blue jewel in the cosmos, an oasis of vibrant life and diversity. Yet its beauty hides a fragile core. We live on a dynamic planet, subject to cosmic and geological forces that, in the blink of an eye, could drastically alter the course of our civilization or even seal our fate. Let us consider the cosmic threats. A large-scale asteroid impact, like the one that wiped out the dinosaurs, is rare, but not impossible. Monitoring and deflecting asteroids is crucial, but not foolproof. A supervolcanic eruption, such as the Toba event 74,000 years ago, could plunge the planet into a prolonged volcanic winter, devastating ecosystems and collapsing civilization. And on a more immediate level, the very fragility of our globalized civilization in the face of uncontrolled pandemics or geopolitical conflicts involving weapons of mass destruction, though terrestrial in origin, poses existential risks to human unity and continuity. Becoming a multi-planetary civilization is not science fiction. It is a vital security strategy. Establishing self-sustaining colonies on other celestial bodies, starting with Mars, would be our ultimate insurance policy. If an uncontrollable cataclysm were to strike Earth, the flame of human civilization would not be extinguished. It would continue to shine on Mars, a testament to our resilience and foresight. This is not about abandoning Earth, our home and cradle, but rather about diversifying our risks, ensuring that humanity's journey goes on, regardless of cosmic whims or terrestrial failures. Additionally, the exponential growth of the human population and the unchecked consumption of resources have placed unprecedented pressure on Earth's ecological systems. While sustainability and conservation are global imperatives, the vision of expanding our presence to another planet offers a unique perspective, the possibility of easing the strain on Earth's resources and the chance to develop new forms of sustainable living in a completely different environment. In this sense, Mars would not only be a refuge, but a planetary-scale laboratory. Here we could refine and test closed-loop technologies, extreme renewable energy systems, and high-efficiency food production methods, innovations that would have revolutionary applications back on Earth. Imagine solutions for water desalination, air purification, and food production in hostile environments, all born from Martian demands, yet offering direct and profound benefits for Earth. The exploratory drive, humanity's unshakable essence. If survival is the pragmatic engine, exploration is the soul of our species. Since our ancestors first looked beyond the next hill, the unknown has called to us. It was this insatiable thirst for knowledge and the desire to venture forth that drove us out of caves, across oceans, and, in the 20th century, to the moon. Mars now stands as the next logical and monumental step in that innate journey. It is the ultimate challenge for our ingenuity, our collaboration, and our determination. The colonization of another planet is the pinnacle of space exploration, a venture that will demand the best of science, engineering, medicine, and, crucially, international cooperation on a scale never before witnessed. And as history has shown us, Every great leap in exploration is a catalyst for innovation. The space race of the 20th century, for example, gave rise to a myriad of technologies we now consider mundane, from water filtration systems and freeze-dried foods to insulation materials, radial tires, GPS navigation systems, and medical imaging technologies. Investment in space exploration is an investment in cascading progress. The colonization of Mars, an infinitely more complex and demanding enterprise, would drive technological advancements in fields such as artificial intelligence, for automation and data analysis in extreme environments, autonomous robotics for construction and maintenance without constant human presence, biotechnology for life support systems and food cultivation, renewable energy and compact nuclear power systems to ensure reliable energy sources, advanced materials, lighter, stronger, and capable of withstanding radiation and extreme temperatures, and space medicine, to understand and mitigate the effects of microgravity and radiation on the human body. Each challenge that must be overcome for life on Mars would generate applicable solutions and tangible benefits here on Earth, driving the global economy, creating new industries, and generating high-skilled jobs. It is a bet on the future, where return on investment is measured not just in dollars, but in knowledge, capability, and resilience. The promise of a future beyond limits, redefining what it means to be human. Mars does not offer just a plan B or a scientific lab. It offers the promise of a new beginning, a blank slate. For the first colonists, it would be an unprecedented opportunity to build a society from the ground up, learning from Earth's mistakes and redefining what it truly means to be human. Imagine a society not limited by geographic borders or entrenched ideologies, but united by a shared purpose: survival and prosperity on an alien world. It would be a grand social and political experiment, where new forms of governance, scarcity-driven economies, and human interaction would be shaped by necessity and collaboration. A community of pioneers, driven by meritocracy and innovation, where mutual dependence would forge stronger bonds, and the values of science, exploration, and sustainability would be deeply embedded in its very existence. Moreover, the human presence on Mars would unlock scientific discovery on an unprecedented scale. The planet is a vast laboratory waiting to be explored. We already have substantial evidence of frozen water in its polar ice caps and underground, a vital resource for colonization. But the greater question still persists. Was there or is there life on Mars? The search for evidence of microbial life, past or present, remains one of the greatest questions in modern science. Colonizing Mars would allow us to investigate these mysteries up close, with human minds and tools, seeking answers to fundamental questions about the origin of life, its distribution across the cosmos, and ultimately, our own cosmic place. A deeper understanding of Martian geology, its complex atmosphere, and its climatic history would provide crucial insight into planetary evolution and the conditions necessary for habitability, not only on Mars, but on distant exoplanets as well. Mars would become a universal classroom, expanding our understanding of life and the universe in ways that only direct human presence can deliver. It is a promise of a new era of discovery, one that transcends the boundaries of our home planet. The price of ambition, the undeniable challenges of conquering Mars. The vision of translucent domed cities and underground farms on Mars is inspiring, but the road to get there is paved with challenges of colossal proportions. Mars is a relentlessly inhospitable planet, and transforming it into a home will require us to overcome obstacles that, until recently, belonged strictly to science fiction. These challenges can be grouped into three crucial pillars: the hostile Martian environment, the complex logistical and technological barriers, and the more subtle, yet equally formidable, human and psychological complexities. The hostile environment of Mars, a cosmic battleground. The first and most visceral barrier is the Martian environment itself, a frozen, dusty, unprotected desert, the exact opposite of Earth's lush biosphere. Thin atmosphere and insufficient pressure. The Martian atmosphere is composed mostly of carbon dioxide, approximately 95%, but is extremely thin. The average surface pressure is only about 0.6% of Earth's sea level pressure. To put it in perspective, that's equivalent to the pressure found 30 kilometers above Earth's surface. Such low pressure means that pure liquid water cannot remain stable on the surface for long. It would either evaporate or freeze almost instantly. For humans, direct exposure to this pressure would cause blood to boil and tissues to swell, a fatal scenario within seconds. Pressurized habitats and robust spacesuits would be a constant requirement for any outdoor activity. The invisible threat of radiation. Unlike Earth, which is protected by a powerful global magnetic field and a thick atmosphere, Mars lacks an effective shield against galactic cosmic radiation and solar particle events. This exposes the surface to significantly higher levels of ionizing radiation. Galactic cosmic rays, composed of high-energy atomic nuclei from outside our solar system, are a constant and penetrating threat. Solar particle events, on the other hand, are unpredictable bursts of high-energy particles emitted by the Sun during solar flares, intense and sporadic in nature. Prolonged exposure to this radiation is extremely harmful to human health, drastically increasing the risk of cancer, causing permanent DNA damage, accelerating cellular aging, and potentially leading to cardiovascular disease, central nervous system damage with cognitive impacts, and immune system disorders. Therefore, Martian habitats would need to be constructed with robust shielding, ideally underground or covered by thick layers of regolith, the Martian soil, which would act as a natural shield. Extreme temperatures and drastic swings. Mars is a planet of thermal extremes. Surface temperatures can drop to -140°C during polar nights and rise to about 20°C at the equator during summer days. However, the daily average remains well below freezing, typically around -63°C. Such brutal thermal variation poses a massive challenge to habitat engineering, requiring highly efficient thermal insulation systems and materials capable of withstanding extreme expansion and contraction cycles without degrading. Furthermore, electronic and robotic equipment must be designed to operate reliably under these harsh conditions. The unpredictable dust storms. Mars is infamous for its vast and ever-present dust storms. They range from small dust devils to global-scale events that can engulf the entire planet for months. Although Martian dust particles are extremely fine, composed mostly of iron oxides which give the planet its reddish hue, they present multiple hazards. They can infiltrate machinery and seals, causing abrasion and mechanical failure, block sunlight for weeks or months, severely affecting solar power generation and crop growth. And if they enter human habitats, they could pose a serious risk to respiratory health. Dust management and mitigation will be a constant obsession in any Martian settlement. The enigma of low gravity. Gravity on Mars is about 38% of Earth's gravity. While this might seem advantageous, colonists would feel lighter and lift heavier objects more easily. The long-term effects of low gravity on the human body are a serious concern and remain largely unknown. Experience in Earth orbit under microgravity has already shown us rapid bone and muscle loss, cardiovascular changes as the heart adapts to pumping less blood against gravity, vision issues, including spaceflight-associated neuroocular syndrome, or SANS, and potential impacts on the immune system. Although Martian gravity is stronger than microgravity, its cumulative effects over decades, especially for children born on Mars, are uncertain. It would be essential to develop rigorous and effective countermeasures, such as daily intense physical exercise, using advanced resistance equipment, specialized diets, and possibly even the implementation of artificial gravity in rotating habitats or centrifuge-based stations in the future to ensure the health and resilience of Martian settlers. Logistical and technological challenges, the scale of engineering and the dream of self-sufficiency. Getting humans to Mars and keeping them alive, productive, and eventually self-sustaining is a feat of engineering and logistics bordering on the epic. Interplanetary travel, a risk-filled odyssey. The journey to Mars takes between 6 and 9 months, depending on orbital alignment, the launch windows that occur every 26 months. During this prolonged period, astronauts would be exposed not only to cosmic radiation, but also to the effects of microgravity until reaching Martian orbit and profound psychological isolation. Spacecraft would need to be developed not only to shield the crew from radiation, but also equipped with highly reliable closed-loop life support systems, advanced medical diagnostics, and living quarters designed to minimize stress and monotony. Communication with Earth, delayed by anywhere from 3 to 22 minutes each way, would make real-time remote assistance impossible. Landing on heavy payloads, the expanded 7 minutes of terror. Landing large amounts of supplies, heavy equipment, and prefabricated habitat modules on the Martian surface is incredibly difficult. Mars has a thin atmosphere, not enough to provide the kind of aerodynamic drag needed to slow down heavy spacecraft as Earth's atmosphere does. This requires a complex and high-risk combination of thermal shields, supersonic parachutes, and deceleration thrusters, all of which must function flawlessly in sequence. The margin for error is razor-thin. Every gram sent to Mars carries an astronomical cost. Estimates range from tens of thousands to hundreds of thousands of United States dollars per kilogram, making mass minimization and load efficiency top priorities. Overcoming this payload bottleneck will be one of the greatest challenges to large-scale colonization. In situ resource utilization, the key to sustainability and independence. The sustainability, and ultimately the independence, of a Martian colony from Earth critically depends on the ability to use local resources. This is known as in situ resource utilization, or ISRU. Instead of bringing everything from Earth, colonists must learn to live off the land. ISRU technologies include water extraction. Water ice is present in polar caps and beneath the Martian surface. It can be heated and purified for use. Water is life, essential for drinking, growing food, hygiene, and crucially, producing oxygen and rocket fuel. Oxygen and fuel production. The carbon dioxide that dominates the Martian atmosphere can be processed, for example, through carbon dioxide electrolysis using the Sabatier process or solid oxide electrolysis to generate breathable oxygen and methane as fuel. This would enable refueling for return trips to Earth and oxygen supply for habitats. NASA's MOXIE experiment aboard the Perseverance rover has already demonstrated the feasibility of oxygen production on Mars. Construction materials. Martian regolith, the planet's soil, can be used as raw material for three-dimensional printing of structures, manufacturing bricks, or shielding against radiation and micrometeoroids. Metals and other elements. In the long term, mining metals and elements from the Martian subsurface would be essential for tool-making, manufacturing parts, and expanding infrastructure. Developing and deploying these extraction and processing technologies on an industrial scale will be one of the most significant technical challenges, requiring advanced robotics, chemical engineering, and robust energy systems. Without ISRU, every gram of material would have to be shipped from Earth, making large-scale colonization economically unviable. Closed life support systems, the artificial ecosystem. On Mars, every drop of water, every molecule of oxygen, and every calorie of food will be precious. Habitats would need to operate using extremely efficient and nearly closed-loop environmental control and life support systems, known as ECLSS. This means recycling water from waste, including urine and sweat, with near-perfect efficiency, purifying air from carbon dioxide and other contaminants, and turning solid waste into nutrients for food production. Failure of any of these systems could have catastrophic consequences for life in the colony. Advanced purification technologies must be developed, along with biological waste recycling systems, such as bioreactors and composting, and food-growing methods in highly controlled, efficient environments. Hydroponics, aeroponics, and aquaponics, all designed to minimize waste. Energy, the lifeblood of Martian civilization. A Martian colony would require a reliable, abundant, and ideally independent energy source. Solar energy is an option, but dust storms and the planet's greater distance from the sun reduce its effectiveness and reliability. More efficient solar panels and autonomous cleaning systems would be necessary. Nuclear energy, specifically fission-based, though controversial on Earth, emerges as a more viable and powerful alternative for a Martian base. Small modular reactors, like NASA's Krusty or kilopower prototypes, could provide continuous sufficient energy for complex operations, including large-scale in-situ resource utilization, habitat heating and pressurization, and vehicle recharging. The safe development and deployment of these energy systems would be fundamental. The human and psychological complexities, the most subtle yet decisive challenge. Beyond physical and technological barriers, there are equally complex and often more subtle challenges related to human physical and mental health. Colonists, physical health adapted to a new world, low gravity and radiation are constant and cumulative threats. Rigorous daily exercise routines, lasting 2 hours or more, would be necessary, along with specialized diets to combat mineral and muscle loss. It may even become essential to develop medications or therapies to mitigate radiation effects. Advanced telemedicine would be crucial, with Earth-based doctors guiding procedures remotely. The ability to perform surgeries using highly autonomous robotic systems, or remotely controlled ones, would be essential, since returning to Earth for treatment in a medical emergency would not be a quick option. The development of biotechnology for rapid and personalized diagnostics, as well as the capacity to conduct biomedical research locally, would be vital. Mental and social health, the psyche at the final frontier. Extreme isolation, confinement in small habitats for extended periods, the lack of natural sunlight and greenery, and the sheer distance from home, all these factors can trigger serious psychological challenges. These include depression, anxiety, disrupted sleep cycles, and most dangerously, interpersonal conflict within the crew. Crew selection must be extremely rigorous, focusing not only on technical skills, but also on psychological resilience, adaptability, communication, and cooperation. Intensive psychological training, scenario-based isolation simulations, regular communication with family and friends on Earth, despite radio delays, and access to recreational activities, hobbies, and private spaces would be vital to maintaining morale and group cohesion. The ability to resolve conflicts constructively will be just as critical as the colonists' technical expertise. Social systems and governance. How do you govern a new world? As the colony grows, complex questions will emerge about how it should be governed. Will it remain an extension of Earth, under the jurisdiction of terrestrial space agencies and governments, or will it evolve into an autonomous entity? with its own laws, social norms, and perhaps even a Martian constitution. Defining rights and responsibilities in such an extreme environment, where the survival of the community may require personal sacrifice, will be a fundamental area of study and debate. Establishing a legal and ethical framework for life on Mars, considering limited resources and the constant need for collaboration, is a challenge that goes far beyond engineering. It is a unique opportunity to reimagine society, but also a potential incubator for conflict if not well planned. The road ahead, an optimistic and realistic path to Mars. Overcoming the immense difficulties of colonizing Mars is not a naive dream. It is an achievable goal, one that will require coordinated and sustained effort on many fronts. It is not just about building bigger rockets or more efficient technologies. It is about rethinking our entire approach to space exploration, fostering global cooperation on an unprecedented scale, and investing heavily in research and development with a long-term vision. Global investment and collaboration, the financial and political levers of Martian conquest. Colonizing Mars is a project that transcends the capabilities of any single nation. It would demand massive, continuous financial investment from governments, private companies, and even philanthropic efforts, on a scale rivaling or exceeding that of the Apollo program or the International Space Station. Public-private partnerships, already growing in the space industry, thanks to companies like SpaceX, Blue Origin, Boeing, Sierra Space, and others, will be absolutely essential. These companies are at the forefront of developing transportation systems, habitat modules, life support technologies, and infrastructure that could make colonization both more feasible and more affordable. Healthy competition among these companies, combined with collaboration with space agencies, is a powerful driver of innovation. But beyond funding, international cooperation is more than desirable. It is indispensable. Space agencies such as the National Aeronautics and Space Administration, United States of America, the European Space Agency, Roscosmos, Russia, depending on the geopolitical context, the China National Space Administration, the Japan Aerospace Exploration Agency, the Indian Space Research Organization, the Brazilian Space Agency, and many others would need to join forces, sharing knowledge, resources, risks, and, crucially, the benefits. This would not only distribute the immense financial burden, but also avoid redundant efforts, harness the best global talent, and promote a more unified and peaceful approach to space exploration. A comprehensive international treaty, going beyond the Outer Space Treaty of 1967, would be needed to define the use and governance of Mars. Questions such as resource ownership, drilling rights, liability for accidents, pollution regulation, and eventually the rights of individuals born on Mars would need to be carefully negotiated. This would help avoid conflict and ensure that exploration and colonization are peaceful, ethical, and sustainable for the benefit of all humankind. The International Space Station is a successful model of collaboration. But Mars will demand an even higher level of cooperation and commitment. Technological advancement, continuous innovation as an imperative. The journey to Mars will require a series of disruptive technological advances, many of which are already in early stages of development. Advanced and faster propulsion. The current travel time, 6 to 9 months, is a major bottleneck. Developing faster and more efficient propulsion systems is crucial. Technologies such as nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant like hydrogen to extreme temperatures to produce thrust, could reduce travel time to 4 or 5 months. Electric propulsion systems, such as ion engines, offer low thrust but are highly fuel-efficient and ideal for cargo missions. In the more distant future, fusion-based propulsion, if controlled nuclear fusion becomes viable, or even more exotic concepts like solar sail propulsion could cut travel time down to weeks. This would drastically reduce radiation exposure and the psychological toll of long-term confinement. Time is quite literally a barrier to life on Mars. Autonomous robotics and artificial intelligence. Before humans arrive to stay, autonomous robots and advanced artificial intelligence systems will be the first settlers and builders. They will be vital during the initial phase of base construction, performing dangerous, repetitive, and monotonous tasks in harsh environments. This includes site preparation, construction of pressurized habitats using three-dimensional printing with Martian regolith, installation of power and communication infrastructure, and the early stages of in-situ resource utilization. Artificial intelligence could optimize resource use, continuously monitor colonists' health and system integrity, predict equipment failures, and assist with scientific exploration and complex decision-making based on large volumes of data. The ability to operate autonomously for long durations without constant human oversight will be a key differentiator. Biotechnology and space medicine, adapting life to a new world. Biotechnology research will be critical for developing high-yield, low-energy agricultural systems in controlled environments, such as hydroponics and aeroponics, capable of producing fresh food and essential nutrients. Genetic engineering could help create crops resistant to extreme conditions or enhanced with optimized nutritional profiles. Advanced biological waste recycling systems would convert waste into usable nutrients and energy. Eventually, small-scale terraforming technologies may emerge, such as the creation of breathable microenvironments or closed, self-sustaining ecosystems. In space medicine, a deeper understanding of the effects of low gravity and radiation on the human body would lead to the development of more effective countermeasures, including new medications, gene therapies, and possibly even bioengineering to adapt the human body to Martian conditions. Personalized medicine and the capacity to perform complex diagnostics and treatments on-site will be essential. Three-dimensional printing and additive manufacturing, building with what you have the ability to print spare parts, tools, and even entire habitat modules on-site using local materials, such as Martian regolith, would dramatically reduce reliance on shipments from Earth. This would make the colony much more resilient and self-sufficient. Large robotic three-dimensional printers could construct thick-walled structures that provide necessary shielding from radiation and micrometeoroids. This technology is a game-changer for long-term sustainability. Infrastructure in space, a new foothold for humanity. To make Martian colonization viable and efficient, robust infrastructure must be built not only on Mars, but also in Earth and lunar orbit. Lunar Gateway and other forward bases. A space station in lunar orbit, like the National Aeronautics and Space Administration's Gateway program, could serve as a refueling, assembly, and testing outpost for missions to Mars. Transport vehicles could be assembled and refueled at the Gateway, using propellant either launched from Earth or eventually extracted from the Moon. Cosmic refueling, exploring and utilizing lunar resources, such as water ice found in polar craters, to produce propellant, hydrogen and oxygen, could drastically reduce the cost of launching missions from Earth. Rather than carrying all the fuel needed from Earth, spacecraft could be refueled in lunar orbit, using resources mined from the Moon. This would turn the Moon into a cosmic gas station, an essential springboard for interplanetary travel. Orbital manufacturing platforms, large spacecraft components or habitat modules that would be impossible to launch fully assembled from Earth, could instead be built or assembled in orbit. This would allow for the creation of far larger and more capable vehicles, designed specifically for the journey to Mars. Developmental phases. A gradual and optimistic approach. The colonization of Mars will not happen overnight. It will be a gradual, methodical process, divided into overlapping stages that build upon each other, driven by optimism and resilience. Accelerated robotic reconnaissance and exploration missions, present to near future. Rovers, such as Curiosity and Perseverance, along with orbital satellites, will continue mapping Mars in unprecedented detail. Their mission, to identify the most promising locations for settlements, areas with access to subsurface water ice, natural topographic protection from radiation, and suitable terrain for construction. Atmospheric and geological data collection will intensify, laying the groundwork for human arrival. Sample return missions, 2030s. Returning Martian rock and soil samples to Earth for in-depth analysis is a critical step. This will allow us to search for evidence of past or present life using more advanced instruments than can currently be sent to Mars. It will also help us better understand the composition of Martian regolith, enabling more efficient development of in-situ resource utilization technologies and accurate assessment of biological risks. Crewed precursor missions and infrastructure testing, 2030s to 2040s. Human crews will be sent for short stays, perhaps lasting several months, to test technologies in real Martian conditions. These astronauts will act as pioneers, assisting robots in building basic infrastructure, digging radiation-shielded shelters, assembling initial habitats, installing power systems, and validating ISRU technologies on-site. This will be a phase of learning and adaptation, with a guaranteed return to Earth. Establishment of the initial permanent base, 2040s to 2050s, the arrival of the first permanent colonists. This initial team, composed of scientists, engineers, medical professionals, and ISRU experts, would live in pressurized and shielded habitats with closed-loop life support systems. Their primary focus would be to validate sustainability systems, expand ISRU capacity, and begin long-term scientific research, preparing the colony for future growth. Colony expansion and transition to self-sufficiency, 2050s to 2070s. As the colony grows, it will become increasingly self-sufficient, producing most of its water, oxygen, food, and building materials from Martian resources. New colonists would arrive in successive waves, each bringing different skills and contributions. Scientific research would deepen. Basic industries would emerge, such as manufacturing components from Martian metals, and the colony would begin evolving into a center of innovation and production. Multigenerational growth and Martian society from the 2070s onward. Over time, the first Martians would be born, citizens of a new world. The colony would evolve into a multi-generational society, developing its own culture, identity, economy, and eventually a more autonomous system of governance. Mars would become humanity's second home, a living testament to our capacity to innovate, adapt, and thrive in even the harshest environments. The colonization of Mars is, without doubt, the greatest challenge humanity has ever dared to face. It is not a utopia nor a fairy tale, but a frontier that demands our utmost courage, intelligence, resilience, and above all, our capacity to collaborate. It is a journey that would force us to evolve, to innovate, and to cooperate as never before. And in doing so, we might not only ensure our long-term survival, but also redefine the future of life and consciousness, spreading the flame of civilization throughout the cosmos. Mars is calling us. And with each rocket launched, each rover that explores, and each scientist who dreams humanity, in its relentless quest for the unknown, prepares to answer. Our optimism lies in our ability to solve problems, to unite in the face of a shared challenge, and to never stop looking toward the stars. Stars, because within them lies not only our past, but more importantly, our future. If you enjoyed this video, leave a like, share your thoughts in the comments, and spread it with others. Subscribe to the channel so you don't miss any new journeys through the cosmos. I am Commander Marcos, and you are watching Stellar Chronicles, where every shadow in space hides a story. Thank you for watching, and until our next stellar curiosity.